Module 3, Unit 6, Glaciers, Deserts, and Winds. The Earth's landscapes are sculpted by a variety of natural forces, including glaciers, deserts, and winds. Each of these forces contributes to the transformation of the surface over time, leaving behind distinct features and geological records. Glaciers, often thought of as slow-moving rivers of ice, play a pivotal role in shaping valleys and redistributing vast amounts of sediment. In arid regions, deserts evolve through the interplay of limited rainfall, intense weathering, and occasional water flows. Meanwhile, winds act as both an agent of erosion and deposition, carving and redistributing materials in ways that leave a lasting imprint on the land. Together, these forces demonstrate the complex and dynamic processes that shape Earth's surface. Glaciers, massive bodies of ice that form in regions where snowfall exceeds melting and evaporation, are among the most powerful agents of erosion and deposition. These ice masses can be divided into two primary types: valley glaciers, which flow through mountain valleys, and ice sheets, which cover vast areas of continents. Ice sheets, such as those found in Antarctica and Greenland, are the largest type of glacier capable of influencing global sea levels. During periods when ice sheets expand, large amounts of water are stored in these glaciers, causing sea levels to drop significantly. The movement of glaciers is driven by the force of gravity, causing them to flow downslope. When a glacier lengthens over time, this indicates that accumulation, the addition of snow and ice, exceeds wastage, the loss of ice through melting and sublimation. As glaciers move, they erode the underlying rock, carving out distinctive U-shaped valleys. This process contrasts with the V-shaped valleys formed by rivers, offering a clear indication of the erosive power of ice. The sediments carried by glaciers, known as glacial till, are deposited when the ice melts, creating features like moraines, drumlins, and outwash plains. The Pleistocene epoch, often referred to as the Ice Age, was a period marked by the extensive growth of glaciers across the planet. These ice sheets not only shaped the physical landscape, but also influenced global climate patterns, sea levels, and ecosystems. The indirect effects of Ice Age glaciers can still be seen today, from the distribution of glacial deposits to the patterns of rivers that were rerouted by advancing ice. While glaciers dominate cold regions, deserts represent the opposite extreme, characterized by arid climates with limited rainfall. Despite the lack of frequent rain, running water plays a surprisingly important role in shaping desert landscapes. When rain does occur, it is often in the form of intense, short-lived storms that generate flash floods, rapidly eroding and depositing material. This process creates features such as alluvial fans and ephemeral streams, which are unique to arid regions. Wind, another key force in desert environments, contributes to both erosion and deposition. However, while wind is often credited with sculpting dramatic landscapes, its role as an agent of erosion is often overstated. Wind is most effective in areas where loose, dry sediments are available for transport, as it can pick up fine particles and carry them over long distances. This process, known as deflation, creates features like desert pavement, where the finer materials are removed, leaving behind a layer of larger, more resistant particles. Wind also shapes sand dunes, depositing material in characteristic patterns, depending on the direction and consistency of the prevailing winds. In contrast to the arid environments of deserts, coastal regions experience erosion primarily through the action of ocean waves, mainly composed of salt water. These waves, driven by the gravitational pull of the moon and the sun, continuously shape shorelines by eroding rock and redistributing sediments. Coastal erosion is a dynamic process, influenced by factors such as wave energy, tidal patterns, and the composition of the coastline. Over time, this process creates landforms such as sea arches, stacks, and wave-cut platforms. The processes of glacial and desert erosion illustrate the fundamental principles of energy and matter. According to the first law of thermodynamics, energy cannot be created or destroyed, only transformed. This principle is evident in the energy transfer that drives natural processes, from the gravitational energy causing glaciers to flow to the kinetic energy of wind shaping desert landscapes. Similarly, the movement of ocean waves and the erosion they cause demonstrate the transformation of energy across different systems. Human activities further intersect with these natural processes, often exacerbating their effects or introducing new challenges. For instance, the reliance on fossil fuels as a non-renewable energy source has contributed to changes in climate patterns, affecting glacier dynamics and desertification. Melting glaciers, accelerated by rising global temperatures, contribute to sea level rise, threatening coastal communities. Similarly, land use changes in desert regions, such as overgrazing and deforestation, can destabilize soils, increasing vulnerability to wind erosion. Groundwater, another critical component of Earth's systems, interacts with these processes in significant ways. Beneath the surface, groundwater is stored in aquifers, layers of rock that can hold and transmit water. The upper surface of the zone of saturation, known as the water table, fluctuates with changes in precipitation and usage. Groundwater plays a vital role in sustaining ecosystems, especially in arid regions where surface water is scarce. In karst landscapes, groundwater dissolves limestone bedrock, creating caves and sinkholes that exemplify the interconnectedness of Earth's systems. As the forces of glaciers, deserts, and winds interact with other natural systems, they create a wide range of landforms and environments that shape life on Earth. Glaciers carve valleys, deposit sediments, and influence global sea levels. Deserts, while seemingly barren, are dynamic landscapes shaped by the interplay of limited rainfall, occasional floods, and persistent winds. Meanwhile, coastal and wind erosion demonstrate the continual reshaping of Earth's surface, driven by the fundamental principles of energy and matter. These processes, though varied in their specifics, share a common thread: the relentless transformation of the planet's surface, guided by the interaction of natural forces. The study of these forces offers not only an understanding of Earth's past, but also insights into its future. As glaciers retreat, deserts expand, and winds redistribute sediments, the planet's landscapes are constantly evolving. By examining these processes, we gain a deeper appreciation for the power and complexity of natural systems, as well as the need to balance human activity with the preservation of Earth's dynamic environments. From the towering ice sheets of the poles to the shifting sands of the deserts, the forces of glaciers, deserts, and winds leave an indelible mark on the planet, reminding us of the ever-changing nature of the world we call home. Unit 7, Plate Tectonics. The theory of plate tectonics stands as one of the most significant advancements in Earth science, offering a comprehensive framework to understand the dynamic processes that shape our planet's surface. This theory explains the lateral motions of Earth's lithospheric plates, vast sections of Earth's rigid outer shell that float atop the semi-fluid asthenosphere. These movements are primarily driven by the transfer of heat from deep within the mantle to the top of the asthenosphere. This heat, generated by the decay of radioactive elements and the residual energy from Earth's formation, creates convection currents in the mantle, pushing and pulling the plates in a constant cycle of motion. The lithosphere is divided into a mosaic of tectonic plates that interact along boundaries, classified as divergent, convergent, or transform. Each type of boundary results in distinctive geological features and processes. At divergent boundaries, plates move apart, creating new oceanic crust as magma rises to fill the gap. This process, known as seafloor spreading, is supported by compelling evidence such as magnetic stripes on the ocean floor. These stripes record the Earth's magnetic field reversals, providing a timeline of crust formation and confirming that ocean basins are not static but continuously renewed. Convergent boundaries, where plates collide, give rise to some of Earth's most dramatic geological features, including mountain ranges, volcanic arcs, and deep ocean trenches. For example, when an oceanic plate subducts beneath a continental plate, the descending plate melts and forms magma, which can lead to volcanic activity. Volcanoes, in this context, are a hallmark of convergent boundaries, though they are not exclusive evidence for plate tectonics, as volcanic activity can occur in other settings, such as hotspots. Transform boundaries, where plates slide past one another, are characterized by strike-slip faults, like the San Andreas Fault in California. These boundaries are often associated with intense seismic activity, as the plates lock and release energy in the form of earthquakes. This lateral movement illustrates the complex interactions between plates and underscores the dynamic nature of Earth's lithosphere. The theory of plate tectonics builds upon earlier ideas, such as the hypothesis of continental drift proposed by Alfred Wegener. Wegener suggested that continents were once joined in a supercontinent called Pangaea and have since drifted apart. Although he lacked a mechanism to explain the movement, his hypothesis laid the groundwork for modern plate tectonics. Today, paleomagnetism, the study of Earth's ancient magnetic field recorded in rocks, provides a robust mechanism to support continental drift and plate movement. Magnetic minerals in solidifying lava align with Earth's magnetic field, preserving a record of its direction and intensity at the time. This evidence, combined with the symmetrical pattern of magnetic stripes on either side of mid-ocean ridges, offers definitive support for seafloor spreading and the mobility of tectonic plates. Hotspots further illustrate the motion of tectonic plates. These localized areas of volcanic activity, caused by plumes of hot mantle material rising to the surface, create volcanic island chains like the Hawaiian Islands. As the Pacific Plate moves over the stationary hotspot, new islands form, while older ones are carried away, providing a visual record of plate movement over time. Ocean floor drilling has also provided critical evidence for plate tectonics. By sampling ocean sediments and basalt from the seafloor, scientists have confirmed that the age of the ocean crust increases with distance from mid-ocean ridges. This pattern aligns with the process of seafloor spreading, demonstrating that new crust forms at divergent boundaries and moves outward over time. The driving forces behind plate tectonics are still a subject of ongoing research, but mantle convection remains the leading explanation. In addition to heat-driven currents, other factors like slab pull and ridge push play significant roles. Slab pull occurs when a dense oceanic plate subducts into the mantle, pulling the trailing plate along with it. Ridge push, on the other hand, arises from the gravitational force exerted by elevated mid-ocean ridges, pushing plates away from divergent boundaries. Together, these forces create a dynamic system that reshapes Earth's surface on a geological timescale. The implications of plate tectonics extend far beyond the formation of geological features. This theory explains the distribution of earthquakes, volcanoes, and mountain ranges and provides insight into the processes that control the Earth's internal heat and material flow. For example, understanding plate interactions helps scientists predict areas at risk of seismic and volcanic activity, contributing to disaster preparedness and mitigation efforts. Regions like the Pacific Ring of Fire, where multiple convergent and transform boundaries intersect, experience frequent earthquakes and eruptions, underscoring the relationship between plate tectonics and natural hazards. The asthenosphere, a ductile layer of the mantle beneath the lithosphere, plays a crucial role in the movement of tectonic plates. Although solid, it behaves plastically over long timescales, allowing the rigid lithosphere to move above it. This interaction between the lithosphere and asthenosphere facilitates the transfer of heat and material, driving the processes that sustain plate tectonics. While the theory of plate tectonics has answered many questions about Earth's dynamic behavior, it also raises new ones. The exact mechanisms driving mantle convection, the variations in plate velocities, and the factors influencing the initiation of subduction zones remain active areas of research. These questions highlight the complexity of Earth's systems and the need for continued exploration.